Ramani Duraiswami again. So my research areas sort of fall into two areas. One is something which sort of overlaps with what Ming mentioned. I work on computational audition. I work on scene capture, scene reproduction, so that you experience an audio scene in its full 3D. I've worked in the past a lot on computer vision and graphics, but now mostly the work I do in vision and graphics is in relation to supporting the audio work. And the other side of my work is in scientific computing, and there I also do numerical analysis and parallel computing, but in support of computational audition. So we have developed various algorithms for the fast solution of the wave and the Helmholtz equation and computing scattering. More recently, just like everybody else, deep learning is such a fantastic tool. We are using it to speed up computations in various ways. And there's applications to game simulations, VR and AR. And a few years ago, we spun out a startup called VisiSonics, which is local in College Park, which has taken some of the fruits of the research via license from the university and is commercializing them. The second area is on fast numerical algorithms. In particular, we focused on a method called the fast multipole method, which achieve order n time and memory simulations for various equations of physics and also for statistics and machine learning. And we've also parallelized this algorithm and sort of distributed them on heterogeneous GPU, CPU computer architectures. These, again, are widely used. So one sort of driving force in my research is the fact that audio is not so widely represented in computer science departments as it should be, even though in our brain, almost the same amount of real estate is devoted to sort of processing of sound as it is to processing of visual things. And many people who work in VR and AR focus only on the visual aspects of things, but when people are in these artificially rendered worlds, if the audio is not correct, the illusion breaks, and you do not want to stay in that VR or AR experience. And so if VR and AR are to become huge and big as people want them to be, they'll have to focus on audio. And also, if you want to build robots which are able to sort of live in the world, you have to use all modalities, not just the visual, for the robot to interact with the world. So I'm just going to highlight 4 aspects of previous work. We developed a camera for sound. So essentially, pixel representations of spatial audio, which we are able to then figure out where sound is coming from. It's now widely used in the auto industry to design quieter cars and by architects to build better rooms. Second is a spatial audio engine, which models propagation in real time, and it's the basis for Oculus VR's 3D audio engine. We've developed a very fast Helmholtz equation solver, which is licensed to a company called ESI, which is now widely used in industry, that software. And finally, a current project, I'm trying to personalize spatial audio to the shape of people's heads and ears by computing or measuring something called the head-related transfer function. And doing this, we have built the largest database for such measurements, which is now ripe for deep learning. So here is a video of our camera for sound. As he snaps his fingers, you see the area light up, and that's the visual representation of the camera. So this actual camera looks like a head-sized sphere. It has 64 microphones and 5 cameras on it, and it's able to capture 3D audio from all directions and create a visual representation. This is a wonderful auditorium, which is at the campus of the university. It's called the Clarice Smith Center. And we went and took that camera into this space and measured how the reverb in that space. So there is a single loud clap from the stage, and you can see all the reflections being sort of, as the sound propagates to that stage, through that space, the reflections of the walls, of the seats, etc. And this is a tool now being used by architects to quieten various halls, including the Sydney Opera House. One interesting thing is everyone has different sized heads, but also different shaped ears, and everyone's ears are different. And because of that, the way you listen to 3D sound is quite different. And if you look to your left and right, you'll see people with different shaped ears. What we want to do is measure a characteristic called the head-related transfer function associated with scattering from their ears. And we developed a very fast method to measure it. I'm just going to skip through this because we don't have time, but it's a cool idea I'll talk to you about later. We've also developed a generalized approach to solve many equations of classical mathematical physics, all based on the fast multipole method. And people have built various solvers. Here is a solver for the Maxwell equations of waves, radar waves coming into a forest. And we're able to simulate the scattering of the trees and off the ground. This is for an area which is about 15 meters by 15 meters, which is a pretty large area. And this is a simulation of smoke rings, again, using the same fast multipole methods. So this is essentially vortex rings going to a wall or going through each other. Some current projects in my group. We're working on a fast algorithm for complex shaped rooms based on an iconal approximation. And that work is done with Professor Masha Cameron in math, with the student Sam Potter, funded by industry. We have fast algorithms for the Maxwell equations in 3D, funded by the Army Research Lab. We are creating a device for the deaf to process auditory environments better, funded by NSF. And this is in combination with various human factors researchers, John Froelich and Leah Findlater, fast personalization of HRTFs I mentioned, and many other projects. So you're welcome to come and look me up, and we move to the next.